Ladies and gentlemen, welcome to the World Professional Automotive Community Lunchtime Series. Today we have Cameron Conover presenting VW Audi Thermal Management. Before we get started, there are a few housekeeping items we need to go over. If you have any questions, please put them in the question box and Cameron will answer as many as time allows at the end of the webinar. If you are attending this webinar as a group and would like individual certificates, please go and register individually during the webinar. Our platform only sends certificates to those who registered. We don't want you to miss out on a certificate if you'd like one. With that said, we're now ready to start. Cameron, take it away.
Thank you, Tanner, and good afternoon to everyone. Hope you're looking forward to learning about thermal management from Volkswagen and Audi. Today I'm going to go through with you kind of what is thermal management, innovative thermal management, what is, where we'll find it, what vehicles we might see it in, theory of operation and use, and a few things to help you diagnose it, and a couple of little common faults. So let's jump in here. So first of all, what vehicles are we going to see innovative thermal management in? And the first implementation of ITM was in the Touareg hybrid. You'll see it in a 4.2 liter V8 TDI engine, 3.6 liter V6 FSI, that's like your VR6 engine. You'll see it in the Gen 3 EA888, which is your 2 liter turbo engine, and the EA888B, which would be the same engine with the Miller cycle, like in the SUVs. You're also going to see that implementation in the supercharged like 3.0 Ts, and pretty much all of the new stuff is going to have some facet of innovative thermal management included. There's a lot that goes into a complete innovative thermal management system. Not all vehicles will have all of the components of ITM, but most of them will have some aspect of it. And then, of course, you're going to see some similar strategies employed by other manufacturers as well. Here's a chart that kind of shows us a few of those different facets of ITM. The main one being stationary coolant. That's a big aspect of ITM that we'll find almost in all of these vehicles. Looks like the only one that doesn't show that is a 3 liter V6 TDI. And we'll talk about what stationary coolant is and why and all that. You have gearbox oil and oil heating. And then we have separation of interior heat circuit and the cab and the HVAC system. So all these things can be separated out thermally, and we'll kind of see how and why. Now, what is innovative thermal management? The innovative thermal management system's objective is to reduce consumption and CO2 emissions via optimized vehicle thermal management. Optimized thermal management means that all thermally strained components and assemblies which are connected to the cooling system, such as the engine or gearbox, are kept within a temperature range which is optimal for their efficiency. Excuse me. So when we talk about the efficiency of these components, like the engine, for example, the efficiency of the engine can be found in a few different ways. One way is thermally, with the viscosity of the oil in the engine, and with the metallurgy, the components and the engine and tolerances and the bearings and things. All of that stuff likes to be at a specific operating temperature, or a good hot operating temperature, in order to be as efficient as possible. Another aspect of efficiency when it comes to the engine is fuel efficiency, just through the aspect of how much fuel we use. So if we run the engine at a very hot temperature, and what happens to the engine when it's very hot? The cylinder head gets hot, and when the cylinder head gets hot, the air charge coming into the engine, that heats up. And when the air heats up, we know that all the molecules in the air spread out. They're less dense when they're hot, right? So all the oxygen molecules are spread out, and you get less oxygen per unit in the air in that engine, in the air charge of that engine. And if we have less oxygen in the air, that means that we can get to a stoichiometric ratio with the fuel by using less fuel as well. So at a low load situation where we don't need to make maximum power, if we run the engine very hot, we can actually spray less fuel and still be stoichiometric and be more efficient in that way. So there's a couple of different ways to think about efficiency when we think about the thermal management of the engines. The ITM system has a software application in the engine control unit that is known as the ITM Thermal Manager. It forms a network between the engine, the gearbox, air conditioning control unit, along with their sensors and actuators. This software is used for optimum distribution of the available engine heat while taking the heating and cooling requirements of the interior engine and gearbox into account. So that is just what it says. Everything's communicating over the CAN network. The ECU has a little application built into its memory and its program that just monitors what available heat is there, how hot is the engine, where is the heat, and what other components might need some heat in order to reach their efficiency. And then they all communicate together, and they can control coolant flow valves and different other valves to control the coolant flow throughout the power plant, the powertrain of the vehicle and into the passenger compartment. The main emphasis was on rapid engine heating, reduction in fuel consumption by rapid and thermodynamically optimized engine temperature regulation, as well as heating of the vehicle interior when required. So rapid engine heating means that we can get down to closed loop, full control of the air-fuel ratio as quick as possible, right? So in order to get up to temp quickly, we want to preserve all the heat in the engine that we can. If you look at the evolution, if we use the 2-liter turbo as an example, and you look at kind of the evolution of how fast the engine and the emission system can get up to temperature, when we talk about the BPY, which is the first direct injected 2-liter turbo that VW and Audi came out with, that belt-driven timing belt one with the exploding high-pressure pump follower, that engine was able to get to closed loop in 40 seconds. So under a minute, just under a minute, down to closed loop, which means the ECU has full control over air-fuel ratio. When we move into the next iteration of the 2-liter turbo, so we're talking about the chain-driven engine, the CBFA was the Sulev version of that engine. So the CBFA engine, the Sulev version, was able to get to closed loop, or is able to get to closed loop in about 20 seconds, right around 20 seconds. So they cut the time to closed loop in half there between BPY and CBFA, with the CCTA being somewhere kind of in the middle because it doesn't have secondary air injection. Now with the Gen 3 EA888 2-liter turbo, the time to close loop on that engine is 9 seconds. Now that's not only due to innovative thermal management. There are other aspects of the design of that engine, such as the electronic wastegate and things like that, that contribute to that fast time to close loop. But the innovative thermal management system in that engine definitely heavily contributes to the ability of that engine to get into closed loop in 9 seconds, which is pretty amazing. We've made some pretty big leaps throughout the evolution of that engine. Now this chart is a chart that shows us the difference between conventional thermostat and the innovative thermal management system over the new European drive cycle. So that NEDC is what they use over in the EU to do their emission standards. And what you see is, and the red line here is vehicle speed. On the bottom, we have time in seconds. And so vehicle speed, we have a lot of stop and start driving at lower speeds. So that would be like in-town type of driving. And then we have a longer drive here that reaches higher speeds without stopping. So that's their complete drive cycle. And we're going to look at the difference between a conventional thermostat and innovative thermal management. So on the right side, you have vehicle speed. On the left side, the left axis here, you have engine temperature. So the the conventional thermostat that we're used to, everybody is very used to this, and a lot of us think this way in terms of conventional thermostats. The engine warms up, and once it gets to operating temperature, it stays at a constant operating temperature. Everything gets kind of saturated with the same amount of heat, and it just manages that heat and stays right there on that level. So in this graph, we see that the conventional thermostat engine is getting up to around 98 degrees Celsius and just staying there. Now, if we look at the dark green line here, that represents innovative thermal management. And we see, first of all, that dark green line, it heats up much quicker. The time to operating temperature, the angle of attack on this line on the graph here is much steeper. So it's getting up to temp a lot quicker. And not only that, once it's up to temperature, the average temperature that it's running at is much hotter, about 10 degrees hotter in Celsius. So 105 degrees Celsius operating temperature, which is over right around 220 degrees Fahrenheit, right? So pretty hot, really. And that is going to all be low load situations where we see a lower demand for power output. And then look what we see when we see the red line at the end of the graph here. You see the red line take that spike. Look what happens to the dark green line. It just dips right down. And that's in real time. So as soon as you start to load the engine, you do an acceleration, you're putting a heavy load on the engine, the coolant temperature drops down. It drops significantly down inside the engine. That's 25 degrees Celsius drop under load there. And then we stay under load for a period of time and then lift off the accelerator and we do a decel. And as soon as we start slowing down, look what happens. That coolant temperature returns right to 105 degrees Celsius right away. So what gives? How can you do that? Obviously there's something big different between innovative thermal management and a standard conventional thermostat. It's more than just now we've made things more complicated. We have electronic parts on there and everything's overcomplicated. It's more than that. There is actual design in here where we can control the heat in the engine that quickly based on load demand. So let's see how we do that. First of all, here we have that this is a graph that shows us the relationship between the control units, and we were talking about that innovative thermal management software app in the ECU. So in the center here we have the ECU. It can control the coolant pump, and it has CAN networks and other networks that talk to all the other control units. So the AC control unit has a coolant shutoff valve, N82. We can turn off coolant flow into the heater core. Same thing with the gearbox control unit. We can control coolant flow into the gearbox oil heater. So once we get the engine up to temp, then after we get to a certain threshold, the ECU will be willing to share some of the heat from the engine with these other components, but not until we've met our goals in the engine. So it's all designed to be as efficient as possible and make everything be able to get to its target temperature as quickly as possible. So if you get in the car and it's nice outside and you don't need heat on, the engine will be able to heat up a lot quicker than if you get in the car and it's cold outside and you turn the heat on. If you turn the heat on, it may take a little bit longer for the engine to get up to operating temperature. On that same cold day, if you leave the heat off, engine's going to be heating up quicker. So let's look at this diagram here is a diagram of a VR6 3.6 liter cooling system. And we see a couple of check valves here to make sure coolant flows in the right directions, and then check valve here. What we see over here are the control units. So we have the engine control unit, the gearbox control unit and then the HVAC control unit. They're all on the CAN bus together talking to each other, and they have controls over these valves. So the HVAC control unit can control the coolant valve flow through the heater core. This is the heater core right here. This is the gearbox control unit. It has control over a valve that controls coolant flow to the gearbox heater. And then the ECU can control several items. Here is the coolant after run pump the coolant auxiliary coolant pump. We also have the main water pump. The water pump is able to be controlled. The flow from the water pump is able to be controlled. So this diagram just shows us all of these components, kind of how they work together and interrelate with each other. Let's look at this water pump on the VR6. So this is these images are of the 3.6 liter VR6. You'll find similar water pumps on the 3.0T supercharged engine and this V6 hybrid engine. So first of all, here we have coolant regulating valve N515, and that's an electronic solenoid, and it controls vacuum flow to a load. So we have this vacuum source here. On this engine, the vacuum source would be the vacuum reservoir in the intake manifold, and that provides vacuum to the solenoid, and then the solenoid can switch on vacuum to the load. The load here is the coolant pump. And then on this solenoid, we also have a vent, because anytime we want to release vacuum, we need to release vacuum to ambient air, which means that we're going to actually pull ambient air into that system, which in some installations can cause issues, by the way. If you pull debris into that system, you could end up with clogs. But anyway, that's why a lot of times there's caps or filters on those vents. That vacuum pump, that vacuum system can pull a vacuum on this diaphragm here. So we have a shutter. This is a shutter, which is basically a round cover that goes over the impeller inside the water pump, and the vacuum will pull that cover up over the water pump and stop the water pump from being able to circulate coolant. So we are able to just turn off coolant flow to the rest of the engine with the vacuum application. When vacuum is released from that water pump, the spring pressure, there's a spring built in, that spring pushes the shutter valve off of the impeller and lets the water pump coolant. So in the event that the vacuum diaphragm tears or rips and can't hold a vacuum, or we're not able to get vacuum to the diaphragm from the system, under spring pressure, that water pump will be held open so that it can constantly flow. So if you lose vacuum here in this water pump, you would see possibly, definitely would see longer time to heat the engine up. It would take longer for the engine to heat up. And then conversely, if this solenoid somehow failed so that it was stuck open, and vacuum was allowed to constantly flow to the water pump, in that case, the engine could overheat because the shutter is stuck down over the impeller of the water pump and not able to pump coolant into the engine. So you could have an overheating problem if that regulating valve sticks open. So what happens with this pump on when are they going to apply it, and what happens on cold start? So that's when they apply it. On cold start, we're going to close off the water pump, and this is that static or stationary coolant aspect that we were talking about at the beginning. So stationary coolant, on cold start, we close off the water pump and no coolant can flow through the engine. It's not able to flow through there. Then once we reach this temperature, 75 degrees Celsius, then it's time to start allowing some more coolant flow into the engine, because we want to make sure that we don't let the engine get too hot. And we need to probably heat up some other coolant so that we can share it with other components in the drivetrain. So at 75 degrees Celsius, the coolant regulating valve is activated several times. They call it mixed phase, and that activates the coolant pump. So they're pulsing it open. They slowly allow some coolant to flow, opens and then closes, opens and then closes, opens and then closes, and allow some coolant to work its way into that engine. If they just applied the water pump and just opened up that water pump and allowed all the coolant to just go, in that case, you could just replace all that coolant in the engine that we've just worked hard to heat up, push all that hot coolant right out of the engine and drop the engine temperature dramatically really fast, and you'd lose your work. So what we need to do is slowly introduce coolant in there to keep the engine temperature in check, but also to allow warmed up hotter coolant to be available for other parts of the drivetrain in order to start heating up other components. All right. This is a look at that solenoid on the VR6. On the VR6, it's located really close to the water pump, just like this. On the 3.0T engine, you'll see there's 4 vacuum solenoids across the back of the intake manifold. You have secondary air injection solenoid. You have one for intake manifold runner control valves. You have one for a coolant valve that's on the coolant flow to the gearbox. And then you have another one which is for the water pump. And those are lined up on the back, and that would be on your Gen 3 3.0T, the later version of that. And it has vacuum regulated coolant pump as well. All right, so this VR6 system uses a lot of vacuum, and we're going to see that we have vacuum solenoids controlling vacuum flow to these shutoff valves, which are rotary valves with a vacuum actuator used to pull a lever and turn a rotary valve and open and close coolant passages. So what you see here is cooling oil valve N471, and that is the valve that is going to control vacuum supply to shutoff valve for gearbox oil heat exchanger. So we have the gearbox oil heat exchanger here. Once we get up to temperature and we get some coolant flowing, a little bit of coolant flowing through the system, and we have some heat available, we'll be able to open up this valve and provide hot coolant to the gearbox heat exchanger to help get the gearbox up to temperature as fast as possible. All right. And so we see that for gearbox, we see it for engine oil cooler and coolant. This would be also coolant for HVAC, going to be controlled in a similar manner. So if we move past the vacuum regulated system, that's kind of the earlier implementation, not quite as far as advanced. We're going to go and look at now what we see in the EA888, the latest, newest 2-liter turbo. That engine, that's what this graphic is from. So this is looking at a picture of the cylinder head. I found an article about this engine in an engineering magazine, and in this article they were explaining all the design and engineering that went into developing the cylinder head. And what you see here is that we have intake manifold built into the cylinder head. So it's cast into the cylinder head. All the intake runners are in there. You have them in pairs, the companion cylinders, 1 and 4 together and 2 and 3 together, and they're built into the head. And then around that, we have a water jacket so that we can harvest the heat from the exhaust manifold. And then right on the back is just a flat flange that the turbo bolts right up to the head. So we're able to pull the heat out of this exhaust manifold, but we have one design consideration that creates a problem here. The water pump on this engine is mechanically driven water pump. And so that water pump is dependent on engine speed in order to pump coolant. And what we know about the EA888 is it's almost universally installed in vehicles with engine start-stop, right? So there's a problem when you are driving along at 3,000 RPM, the engine gets up to 100 Celsius, and then you come up to a stoplight and you stop the car and the engine speed drops to idle first. So the coolant flow, when the engine speed drops, the coolant flow stalls out, slows way down. So it's rushing through these passages around this exhaust manifold, and then the water pump stops moving and it just stops. The engine first drops to idle, it slows down, and then the engine turns off, right? Engine start stop program. And that means that the coolant in the head all just stops dead in its tracks. The problem with that is that now that coolant can't move heat away from the engine. It can't go anywhere, and therefore it's stuck there in that hot engine that was just 100 Celsius, and now it could do what's called flash boil. So as the speed drops and it sits there, it gets heat soaked, everything gets hot, and that coolant could flash boil in the head. So when they designed this engine, they had to design it with that in mind, and in order to avoid that, they had to very carefully design the volume of water that's in each runner of that water jacket around the exhaust manifold, all the amount of water per inch and all that stuff, and then also the distance between the water jacket and the exhaust runners had to be a specific distance. There needs to be X amount of aluminum material in between that exhaust runner and the manifold and the water jacket. And all that design is there in order to ensure that we don't overheat that engine or flash boil that coolant in the cylinder head when the coolant flow stops. So there's a lot of design considerations that go into the system, and it just shows you how much engineering is involved in developing this. It's really pretty cool. So that's the kind of the design behind the cylinder head. Now we're just talking about the mechanically driven water pump, and that's what this is here. So with the innovative thermal management system, we're still using the same water pump that we had on the earlier chain-driven engines. The difference is the thermostat housing that's behind the water pump. The older engines have a thermostat housing with your traditional mechanical thermostat in there with the wax nodule that heats up and expands and opens the thermostat just like old school. Well, now we have an electronically controlled valve that acts as that thermostat. And this drive belt is running off of the balance shaft on the intake side of the engine. So we have a balance shaft here, and it's running right here on this toothed belt. There's no timing to consider on this belt. It's just running the water pump, but it does run off the balance shaft there on the front of the engine. Here's an exploded view of this water pump. This is actually the thermostat housing or the thermal management module. And what we see here is we have an electric motor right here, and it has a worm drive gear that drives this gear and rotates the rotary slide valve number 1. And that's this drum right here. So we have this round drum that sits inside the housing, and there's an electric stepper motor that can rotate that drum back and forth. And that drum has ports, holes, and grooves cut into it that control coolant flow. So the angle of that, as it lines up with each port, you have a port here, a bypass port coming back from the turbo. You have a port here. This port goes to the outlet of the radiator. You have another port for the inlet of the radiator. You have a port back here that allows coolant to flow from the oil cooler into the thermostat housing. That's this guy back here. All of this stuff can be controlled by rotary slide valve number 1. So the angle that that valve is at dictates how much coolant can flow, or if any coolant can flow back through those ports. And that's how it does its thermostatic control. The other thing that rotary slide valve 1 does is it interfaces with this lantern gear here that runs rotary slide valve number 2. So rotary slide valve number 2's job is to control coolant flow into the cylinder head. So that controls coolant flow from the water pump itself, and not to the cylinder head, but the block. It's mounted on the block below the cylinder head, and it pumps coolant into the block, and that rotary slide valve number 2 can turn that coolant completely off or open it to any degree. So that's how we implement static coolant or stationary coolant in this system. Instead of having a shutter valve that goes down over the impeller of the water pump, we just have the outlet of the water pump is able to be controlled on and off. So that's how that works. And then we have inside this thermostat housing, these are little seals. So number 9 here, these things here, this one, they're seals that are spring-loaded seals that push down onto that drum that interface with each port on the housing and control coolant flow through those ports, in and out of those ports. There's a little cutaway of the thermal management unit. You can see the electric motor here. On the end here is the position sensor. So there's this position sensor built into the end of the thermal management unit that can tell the ECU what angle that rotary slide valve is at. So there's your electrical connector down here, and that's the position sensor. Here's a really good look at the rotary slide valve number 1. That's what it looks like. You can see here these spring-loaded seals that push up against the valve. And you got a really nice look at the port on the valve. And when you look at that port, you can notice that it has a V-shaped groove on it. So it can be wide open, or it can taper down to a smaller hole, or you just turn it in all the way until it's just hitting metal and there's no hole at all and it's closed. So that's how they can control, like, from basically wide open all the way down to partial and then down to closed. And there's these grooves back here are the interface for that lantern gear that turns rotary slide valve number 2, and that's what this is back here. Okay. So this is the recirculation pump V50, and I'm sure you're familiar with these. On the earlier 2-liter turbo engines, we found them down on the front of the block, right behind the AC compressor near the intake tube, and those pulled coolant after the engine was turned off. They pulled coolant from the radiator and pushed it up to the turbo and then back into the water jacket. And that was the reverse direction of coolant flow. So they kind of, after the engine shuts off, they get some coolant out of the radiator and push it through the turbo and back into the water jacket. Well, this one has been moved. So on these engines, the coolant recirculation valve is now located in front of the heater core. So we actually push coolant through the heater core and then to the turbo and then back into the rest of the system. So it's a little different arrangement, a different location. You'll find the valve now located near the back of the head or on transverse. It will be kind of underneath the cold side of the turbo, right near the heater core. So it's moved around a bit. This is a coolant control valve. So we've saw these in diagrams. We've seen a couple of pictures of them, but this is what they look like. They're an electric solenoid valve that has a piston with a rubber O-ring on it. And these valves control the coolant flow. They're just basically activated or not activated, and they control coolant flow to things like the HVAC and to things like the gearbox oil cooler. And these things do have a couple of issues that you should know about. One of them is that the O-ring that seals the piston is not tolerant of engine oil or oils. And so this might sound familiar to some of you guys if you've been working on these things for a while and you remember the problems with the water pump on the earlier ones. The same thing here. If that coolant gets contaminated with oil, the O-ring could swell up and it jams this valve shut. And one of the most common problems resulting from this is customer complaint of no heat. So if you have a situation where somebody comes in and they say, my heat doesn't get hot, you want to make sure that coolant is actually flowing through there. And if it's not, that's your number one suspect right there. So those things do get jammed and create that issue. Another thing that happens with these that we're starting to see happen with these electronic valves is the old dreaded coolant migration. And coolant migration means that the coolant works its way past the internal seals in this valve. It goes past the solenoid, the windings and everything, and it finds its way through the electrical connector out into the wiring harness. And when it gets in the wiring harness, through capillary action, it's wicked away, and the coolant follows the wiring harness around the car until it finds something to ruin. So it'll go into the ECU connector and get a bunch of coolant and water in there and start causing corrosion in the ECU connector and things like that. So that's something to keep an eye on these vehicles, as well as look out for coolant migration on some of these electronic controls on the innovative thermal management system. Now let's talk about some more theory of operation on this system. And this graph, it shows us the different ranges that the ECU runs the engine in, temperature ranges that it runs the engine in based on engine load. So this looks a lot like a dyno chart right here. So if you see, it has engine speed across the bottom, got engine speed down here, and then on the left side we have torque. So how much torque equals how much load there is, right? So if there's a higher torque, that's a higher load on the engine. And then this little key right here shows us temperature ranges. So if you'll notice, at the low RPM and the lowest torque level, our initial temperature range for around idle and low RPM, 105 Celsius, 221 degrees Fahrenheit, right? So that's pretty hot. And again, that's to make it more efficient. That's creating efficiencies because of all the viscosities and all the thermal properties of the engine and the thermal properties of the air coming into the engine. And then we notice that as the load and the RPM increase, we get cooler and cooler. So when we get to the top level here, we're at the highest load and the highest RPM range, we're down to 85 degrees Celsius or 185 Fahrenheit. So you can see all these ranges and these steps that the ECU changes the engine temperature based on load. And so in order to quickly change the engine temperature like that, there must be a trick up its sleeve, because it's not working like old conventional thermostat where everything was the same temperature, right? This graph shows us a little bit about the different steps that the ECU will take with the cooling system on startup and running. So across the top here, we have adjustment angle. And what we're talking about here is the adjustment angle of that rotary slide valve, right? And we kind of start out here in the middle. Cold start is right here. And we have static coolant, stationary coolant. That's the first stage of warm up. So rotary slide valve number 2 is closed and no coolant is flowing through the block or the water jacket around the combustion chambers or anything. No coolant flow at all. Then the next stage we get to is mini volume stream. Mini volume stream means we're cracking open that rotary slide valve number 2 and allowing some coolant to start flowing into the engine. Just like we were talking about with that pulsed pump, we're gonna let some coolant in. We need to control the temperature in the water jacket, but we also need to create some extra coolant flow so that we can heat up other components. Once we get to that phase, we get up to the next temperature range, then we're going to switch on the engine oil cooler, and we do that with another degree of rotation of rotary slide valve number 1. And we open up the port so that you know the oil cooler is on the engine subframe, the oil filter subframe. You got the oil filter on top, canister filter up there on top. Then underneath that is the subframe, and the oil cooler is mounted right to the side of that. And then we have an outlet from that oil cooler that goes straight into the thermostat housing. Well, the inlet into the thermostat housing is opened and closed by rotary slide valve number 1. So we get up to a certain temperature, rotary slide valve number 1 opens, that port on the oil cooler, and it allows coolant to flow from the water jacket around the engine into the oil cooler, and it starts heating up the oil. So we get to that phase where now, okay, now we need to start putting some heat into the oil. Then around the same time period, we would have other valves. This graph is only showing us rotary slide valve action, but we would have another valve that controls coolant flow through the gearbox. If we have a DSG, or if we have a automatic 09G box or something like that on the engine, we're going to heat up that oil in the gearbox. So then there'll be another outboard valve that will open right around that same time period to start heating up the gearbox. Then we graduate into the temperature control range for partial and full load. That is referencing that range that we had in that graph that we just looked at that looked like a dyno chart, from 221 degrees Fahrenheit, 105 Celsius, up to 185 degrees Fahrenheit or 85 Celsius. So that whole range. And that's what this 85 degrees of adjustment right here is, opening and closing those ports to various degrees. We have that V-shaped groove, and we can open and close those ports to control how much coolant can flow from the radiator into the block through the water pump and control the heat of the engine. Now, in order to cool down that engine in a split second like we saw in that graph, we're going to have some coolant that's not as hot as all the other coolant, right? So let's look at this. This is a graph that I made. I used VCDS, which is a scan tool, aftermarket scan tool that's a great diagnostic tool for Audi and Volkswagen, as well as some other associated makes. VCDS, and it has a logging function. So I went in and I selected these PIDs here, and I did a log with them, and then it saves the log in a CSV file. So you have comma separated variables, which is spreadsheet action. So then you open this, you can open that log up in Excel and make a graph with Excel, and that's what I did here. So this is just using Excel spreadsheet graphing, and popped all that data in there. Once you get done with your drive, you pop it in there and you can look and see what's actually going on. So let's look at what I've graphed here. So what we have is the red line is coolant temperature, and that's going to be your standard coolant temperature PID that you see on any scan tool. Then we have the blue line, coolant temperature at radiator outlet actual value. Okay, there's two different coolant temperatures. Then we have the dark yellow line, this darker, I don't know why I ended up with two yellow lines here. I need to get better graphing. So dark yellow is engine temperature management actuator actual value angle. So that's the reading from the position sensor on a thermal management module, okay? So that's this squared off line here. That's that line. All right, the green line is vehicle speed. That's kind of self-explanatory. How fast are we going in kilometers per hour? Over 120, whatever that is. And then yellow line, engine oil temperature. And then we have this other gray line here, this dark light gray line, engine temp management actuator duty cycle for activation. It's a very interesting thing to look at, because you have the ECU telling the thermal management unit, move the rotary slide valve. That's basically what that represents. The ECU command to move the rotary slide valve. So this is a cold start, 20 degrees Celsius. I started the log before I cranked the engine. So we got 20 degrees Celsius here. Then as soon as I crank the engine, the ECU says, oh, hey, this is going to be a cold start, so we need to move rotary slide valve into static coolant. So you see this command right off the bat, bam, right here, a command, rotary slide valve moves up to that position, we're in static coolant. And what we see is no coolant flowing, and the engine temperature, coolant temperature, the red line, shoots up real fast, right? You can see vehicle speed, so pulling out and going down the road to the next stop sign, get ready to leave the neighborhood, and there's vehicle speed. And by the time we get down to the stop sign, we have already almost 60 degrees Celsius in the engine. Once we reach that point, the ECU says, oh, hey, now we can do mini volume stream. So what do we see? Another command right here. Okay, let's go to mini volume stream. And then what happens? Right away, the rotary slide valve moves into the next phase, which is right here, and that's going to represent mini volume stream. Okay. The coolant temperature in the engine continues to rise up, almost up to 90 something degrees Celsius right here. In the meantime, coolant temperature at radiator outlet has basically done nothing, because all of the coolant flow represented by these first two stages here, all of that, it's either no coolant flow or a little bit of coolant flow that only flows through the water jacket in the block. That's all it's doing, is circulating some coolant through the water jacket of the block, because none of the ports on the thermal management module are open yet. So then we get up here around 95 Celsius or whatever it is, and the ECU is like, okay, that's good. So now I'm going to command you again. And guess what it does this time? It turns on the engine oil heater, opens the port for the oil cooler, returning coolant into the thermal management unit or the thermostat housing. So you see the command here. You see rotary slide valve not spontaneously, instantly synchronized right away. Rotary slide valve number 2 moves, and you see almost immediately oil temp rising. Look at that. This line is oil temperature. As soon as we open that port, bam, we start putting heat in the oil too. Okay. Then we see we've got a bunch of little commands here on rotary slide valve. Engine management actuator makes a command, it moves, makes a command, everything moves, makes a command, we're moving, responding to loads. So let's look at vehicle speed. We're kind of cruising down the road here. We're doing 100 kph, and engine temperature gets up to 100 Celsius. So that's 212 degrees Fahrenheit, right? And then the nut behind the wheel opens the throttle wide open. Engine load spikes up. As soon as the engine load spikes up, look what happens to coolant temperature. Bam, drop right down. We're down to like 85 degrees Celsius now. You can see as soon as the load hits, coolant temperature drops, and we move some heat into the radiator. So that's how that response to vary engine temperature by load is possible. We have a huge difference between the heat that's in the radiator, or the heat that's in the engine. The engine's a lot hotter. There's a huge giant difference. Right here we're looking at let's say that's 25 and that's 175 degrees Celsius difference, the delta between engine temp and radiator temperature. That means we have a whole bunch of massive coolant on hand that we can throw on that fire and cool it down so that we can have colder air charge and avoid the dreaded detonation, right? So how we're going to make more power is by cooling off the air, having more dense air, but also one of the biggest ways to make more power is advanced ignition timing, right? On a gasoline engine. So we're going to advance the ignition timing, and that creates more power, but it also creates an opportunity for detonation. Detonation happens when the combustion chamber is too hot. So we're going to cool this cylinder head down and get it down close to 80 Celsius, as close as we can. Cool that cylinder head down, and that helps us avoid detonation in the engine just by having a cooler combustion chamber, and it allows us then to go in with more ignition timing and more advanced and make more power. All right. So some really good diagnostic tools here. If you suspect that you have a failed thermal management unit, you can jump in and just log or look at these live, and when you see, this is going to happen so fast that you're not going to notice it. Really helpful to log these little, this channel for duty cycle, because look at what you see here, 99% of the time it's 0. And then it's going to happen so fast that you might not even notice it with your eyes. So it's important to log this. So you'll see that ECU make the command. You need to see also right away the position sensor is moving. You see the rotary slide valve move, and you know that things are working properly. If you see the commands going and rotary slide valve's not doing anything, or it's moving a little bit and it's keep trying to command it, that thing might be jammed up. Or you might see no movement from the rotary slide valve. You know it's jammed, or you know that the sensor is broken or wires are unplugged or whatever. Okay, couple of more graphs. We got plenty of time here, guys, no problem. So this graph here is another drive, another cold start graph, but I logged a couple of different things. So the brown line again is that rotary slide valve, engine temp management actuator actual value. The yellow line is vehicle speed. The gray line is engine temperature. This blue line is radiator outlet coolant temperature. The green line is the radiator fan activation. And then we have a dark blue line here, these square, looking like a square wave here, the square lines, that is piston cooling jet activation between 0 and 1 right there. You see that? So it's kind of interesting to see what happens. These engines have switchable piston cooling jets. So in earlier versions of the engine, we had piston cooling jets, and these are oil spray jets that just face up at the bottom of the pistons on each cylinder, and all their job is to do is spray oil on the bottom of the piston, and that helps cool the piston off. Again, we're avoiding detonation by keeping the pistons from being hot, which allows us to advance timing and not crack a piston in half. But if we're constantly just spraying coolant into these, spraying oil onto the pistons, and that therefore gets on the rotating assembly and windage happens. Windage means oil is wrapped around the crank and everything, and that creates parasitic drag, which reduces efficiency. So now we have controllable piston cooling jets, and they come on at high load. So you see an acceleration here, piston cooling jet comes on. An acceleration here, piston cooling jet comes on. Acceleration here, piston cooling jet comes on. Over and over and over. So you can see that that's another function of this thermal management theory and efficiency. Another step towards efficiency. It's like, what do they call it? Dying from 1,000 cuts, but you take a little bit away each time, and all these tiny little additions make a big change. The other thing to note here is that the radiator fan doesn't ever even move. We only get up to 85 Celsius here, but still radiator fan never moves, and coolant temperature at the radiator outlet stays ambient the whole entire time on this graph. Here's one more graph for you. This one is a long highway drive. So this is a ton more samples. This is a lot more time condensed into the same looking graph. So it's kind of more spread out, not spread out, but more condensed, and shows a lot more time. So what we see is vehicle speed in yellow, engine speed or RPM is on orange. Coolant temperature is this light gray line. The brown line is thermal management module, right? Rotary slide valve. The blue line is coolant temp on radiator outlet, and the green line are the fans. So check out the fans again, still not moving. I actually had a call from a friend of mine who owns a shop here in town in Greensboro, and one of his techs was trying to figure out what was wrong with the set of fans on a GTI, or how come the fans wouldn't come on. He'd already replaced the fans and they still weren't coming on. And so I came over to try to help him diagnose the thing. And I said, you know, what's going on? Show me what's happening. And he's just got out his Snap-on scan tool and he said, look, it's 200 degrees and the fans aren't on. Something's wrong. And I told him, hey, there's nothing wrong. You're only seeing half of the picture here because the radiator is not hot. So you're fixing something that's not broken. So it's very important to understand how this all works so that we don't get caught in this weird loop of trying to fix something that's not broken. Anyway, you can also see here very good that when I do an acceleration, we're cruising down I-40 in North Carolina, and you can see thermal management module moving back and forth, and look at the coolant temp, it's moving back and forth as the load changes. We're changing between loads, maybe going up and down hills or whatever. And the thermal management module is kind of constantly adjusting the coolant temperature in the engine based on load. Then I get stuck, I come up behind an 18-wheeler, a big truck, a lorry in the road, and I want to go around him because he's going slow. So I accelerate, the transmission kicks down, RPM jumps way up, and I do an acceleration and look at coolant temp right here. It's up here over 100 Celsius. And as soon as we accelerate, it drops down here around 90, right? Look where the heat goes. Now the radiator outlet coolant temperature rises up. The heat gets moved into the radiator. As soon as I decelerate, we decel, and then before too long, coolant's right back up to 100 Celsius again. And look what happens to the coolant in the radiator, right back down to ambient. We're below 20 Celsius. Nice ambient temperature. It happens again. You get behind another truck, you do another acceleration, coolant temp drops, coolant heat is moved into the radiator, and then it's scrubbed off. Never use the fans at all. All right. Just a couple more minutes, guys. We're going to get there, and I won't hold you too long. Just want to show you a few more things, and then we'll be good. So this is a screenshot from VCDS. This is advanced measuring blocks. When we're in this, newer vehicles are using UDS, which is the new CAN protocol. So UDS system doesn't have groups of measuring blocks like we're used to with the older cars. So the groups are gone. We used to be able to get 3 groups of 4 values, right? When they were all like, you had to choose a group and it was 4 different things, and choose another group. And so you could get 12 things on the screen to look at. Well, it's similar now because we still have 12 things to look at, but you're not tied into a group. You can choose any one value that you want. So let's look at some of the values that are appropriate to look at here for diagnosing this coolant innovative thermal management system. Obviously, we want to look at coolant temperature. This is the coolant temperature of the engine. And we have to know coolant temperature of the radiator outlet so we know the full picture, whether we're overheating or not. Engine oil temperature is interesting. Coolant fan activation, coolant shutoff valve, coolant recirculation pump. This PID is really a really good one because it gives us the whole picture of coolant temperatures in one line. So you have engine coolant temperature number 1, which is this coolant temperature of the engine, and then engine coolant temperature number 2, and that's the second one. That's the radiator outlet coolant temperature. If you look at these values, you see that these 2 coolant temps are really close to each other right now. This is after the vehicle has been shut down. So I went on a drive, I parked it, shut it down, and those 2 temps start to come together. And I have something to show you that shows you how and why. Okay, and then really interesting here, engine temperature management actuator actual value of rotation. So that's rotary slide valve position, right? And then this is that one, the gray line with the little spikes, engine temperature management actuator duty cycle. See, it's 0%. Those 2 are the ones that are going to tell you whether or not that thermal management module is working properly. If the ECU tells it to move, it needs to move. Okay, so that's VCDS using UDS system. This is another slide that I put in here because this system can be kind of a bear. In this advanced measuring blocks, when you go in to select your channels, it shows you like 1,000 and something PIDs. You got so many variables, it's insane. You can sit there for an hour just looking through each one and looking to see what it does and see what it did, you know, put it in the graph. So a couple of things to help you do that quicker. First of all, you got a search box here. So I typed in cool, and that gives me coolant temperature, anything with the word cool in it pops up, and then I can go through and select each box to what I want to see. Once you get your list ready and you have all your selections made, and you've made, okay, I've got this profile that I want to look at to diagnose this innovative thermal management system, or I got a profile that I want to look at to diagnose cam timing, or I got a profile to look at fuel trims and fuel pressures. You can go in, click right here. See this, what it says? Click for selection, save, load. Click right there, and you select that, and you say, okay, this is the cooling system testing. This is fuel trims. This is cam timing. Save that. Next time you go back to the car with the same engine, pop that sucker open, and right away you get your list, and you don't have to hunt and peck through everything to try to find all that stuff. All right, just a couple more. This is after parking the vehicle for 5 minutes. So driving down the highway, get off on the exit, go into a store, get a drink, whatever you want to do in the store, and then this is what happens. I came back out to the vehicle after a few minutes, and you can see what's going on now is the fans are on. This great green line is the fans again. Fans are on, but look at the coolant temperatures. Now we've dropped down here to like 90, but the radiator outlet coolant temperature is all the way up to 75. So when we put the vehicle, when we shut the vehicle down and stop it, the coolant temperatures start to merge together, because what we're doing is we're trying to keep the engine from heat soaking. We're trying to manage this post-running heat, and we want to keep the turbo from overheating and coking up the turbo with burned up oil and all of that stuff. So we need to pump a bunch of heat out of the engine and get rid of it. So that's what's happening. We're going to pump heat out of the engine. It ends up in the radiator, and the fans come on to get rid of that heat and blow it out. Then I crank the engine up, start it up, and back out of the parking spot, go back down the road to get on the on-ramp, and this is a highway on-ramp acceleration right here. So look what happens. By the time I get to the on-ramp, we're almost back to 100 degrees Celsius. I do this long acceleration, coolant temp drops right there, right in line with that acceleration. Move a little bit of heat into the radiator, and then as soon as we get up to temp, everything settles out. Up to speed. We get up to speed, things settle out. We're now cruising at a lower load. Coolant temp can go back up. It rises back up to 100 Celsius, and look what happens in the radiator. Coolant temp of the radiator drops all the way back down to ambient, almost to 20 Celsius, and the fans are off again. So we don't even need them. Here we have the vacuum cooling system filler. This is a critical tool that you need to have. This tool pulls all the air out of the cooling system and allows you to quickly replace it with coolant. And you have, this is the factory tool. All the tool trucks have these. You can get them online, everywhere. Cooling system fillers. Because of all the valves, electronic valves, the rotary slide valves, all these valves in the system, it would be easy to have tons of air pockets in the system. So we use this vacuum cooling system filler to pull all the air out. When you have 25 inches of mercury, that means you have very little to no air in that system. Pull all the air out of it, and then allow it to pull just coolant back in, fill it up. That allows you to avoid having air pockets in the system and fill that system with nice fresh coolant in just about 3 minutes. Whereas if you tried to do it the old school way, or with one of those big funnels or whatever, you're going to sit there and let it burp and bubble and waste away 30 minutes that you could be otherwise making money. And when you get done with that, you're still not 100% sure that there's no air, are you? You're not. If you pull a vacuum, there's no air. This shows us the coolant cutoff valve here on the end of the head on a Gen 3. And look at this. This is the high, I call it the high line. It's like the high up bleed off line for the cooling system. So all these components have this small diameter line that connects here, and that allows you, that helps you to be able to pull air out of the system. So you know you're pulling it out of this cutoff valve. You're pulling air out of the top of the radiator. You pull air out of the top of the heater core. You pull air out of the end of the cylinder head, and all that stuff comes to the expansion tank, and you're able to pull it out. And that's how that vacuum cooling system filler helps you. I threw this in here. This is the water pump thermostat housing failure, traditional thermostat housing failure, just to be aware of. When you have these failures, it's because of oil leaks. The oil leak is either going to be coming from the timing cover or from the cam cover. You need to fix those oil leaks when you fix that thermostat housing. One more thing to tell you about vacuum cooling system fillers. On this vehicle, this is a TSB from Volkswagen about the Atlas. The Atlas tells you, this TSB tells you that the Atlas has, you might run into this heater support pump dry running P194AO coolant pump RPM too high. That's because of air in the cooling system. And these cars have this auxiliary rear heat, and they have long coolant lines. And in order to get all the air out of there, you need to use a vacuum cooling system filler, but they also want you to raise the front of the vehicle up higher than the rear of the vehicle. If there can be air trapped in there, especially if you have some coolant left in there and it finds a nice little place to stop airflow. Raise the front of the vehicle up a little bit higher than the rear, and then you can pull all the air out of the system and refill it, and that helps you avoid this problem with the dry running pump. Okay, just one more thing. The future, right? We're not all the way there yet. There's still more future to come. So we have this now. This is kind of where we are. This is thermal management modules. This documentation was created by the company that designed and produces these modules for the OEMs. And this is basically what we have on these Gen 3 cars right here. The next iteration could be this, where instead of having rotary slide valve number 1 dictate the position of rotary slide valve number 2, they each have their own controls and own position sensors so that they can operate independently. And then we move into a more dispersed system where we have small valves located around the car, around the powertrain, and even smaller valves in the cylinder block that control coolant flow on their own without having to have one centralized module where everything returns to that module and is controlled by one module. You could have the valving dispersed throughout the system. All this stuff is going to stay with us. Even when ICE, internal combustion, goes away and we move into EV, we're still going to have thermal management is still going to be a thing that we have to deal with, because the batteries in EVs need to be at a certain temperature in order to operate most efficiently. They don't want to be too hot. They don't want to be too cold. They need to be right in the happy spot so that they can charge and discharge efficiently. And that means that they're going to have thermal management systems to heat them up when they're cold and cool them off when they're hot. And a lot of these same components and a lot of the same theory of operation is going to come along from this kind of setup into that EV stuff. So a lot of this is good stuff to know and keep up with, because it's not going away anywhere, even when we get rid of gas. So that's it for me. And if you, I'll turn it over to Tanner if you guys have any questions. Yeah.
Awesome, great job. We don't have any questions that have came in, and a little bit over, so I know some of these guys are trying to run back and get back to work.
Yep.
So ladies and gentlemen, if you would, there's going to be a survey at the end of this. Please fill that out for us. That lets us know what you like, dislike, and what you'd like to see in the future. Also, please don't forget to hop on to the WorldPAC website and check out the upcoming lunchtime webinars we have, as well as the live virtual classes. Also, if you come up with any questions after this is over, please shoot them over to WTI@worldpac.com. Put class title LTT93 in the subject line, and we'll get them sent over to Cameron to answer. Anything else you'd like to add?
Nope, just have a good day, everybody. Thanks for coming out.
Alrighty, awesome. Have a great day, everyone.